Where there is no non-conservative force acting on a system, the total mechanical energy, kinetic plus potential, of the system does not change. The law of conservation of energy follows from the work-energy theorem. Recall the work-energy theorem. Work net is equal to the change in kinetic energy. Since forces fall into one of two categories, the net or total, work done on an object can be broken into two parts. Work net is equal to the work done by a conservative force and the work done by a non-conservative force, where work conservative represents work done by conservative forces acting on the system, and work non-conservative force represents the work done by non-conservative forces acting on the system. However, we can express the work done on the object by conservative forces in terms of the change in potential energy of the object. Work done by a conservative force equals minus change in potential energy. If we define the sum of an object's potential and kinetic energies to be the mechanical energy of the object, total energy equals kinetic energy plus potential energy, we can rewrite our expression in terms of the mechanical energy of the object. That is, work done by non-conservative forces results in a change in the mechanical energy of a system. This is the generalized work-energy theorem. We now see what is meant by the term conservative force. A conservative force is one which does not change the mechanical energy of an object when the object is moved through a closed path. A conservative force is a force which conserves mechanical energy. It doesn't matter what path you take to get up to a certain height, a force applied against gravity is conserved. However, if you have to slide an object along the floor, you are doing work against a non-conservative force, such as the frictional force of the floor. This force is a path-dependent force and is known as a non-conservative force. You should be able to solve energy problems if you have a scenario like the one described here. Let's look at the steps to solve this problem. Step 1. On the diagram, indicate various states that the system can be in and label them 1 and 2. Step 2. Pick a reference level for y. This is the vertical level at which y equals 0. Typically, it is best to pick the lowest level in the system if it is known. Step 3. In each state, label the following: velocity, vertical position with respect to the reference, and compression in the spring, if any. Note, lowercase x is not the horizontal position of the object. Step 4. Calculate the various forms of mechanical energy in each state: kinetic energy, gravitational potential energy, and spring potential energy, if any. Step 5. Calculate the work done by non-conservative forces, such as friction, in going from one state to the next. Step 6. Set up the work-energy theorem between states 1 and 2. Solve the work-energy equation set up in step 6 to obtain the unknown quantity. A 5-kilogram object is launched from the top of a 35-meter tall building at 10 meters per second, directed at 30 degrees above the horizontal. Assuming air resistance can be ignored, how fast is the object traveling when it strikes the level ground below? Work this problem on your own using energy methods. A 2-kilogram block starts from the top of a 7.5-meter long frictionless ramp, which is elevated at 25 degrees. At the bottom of the incline, the block slides onto a horizontal surface, where the coefficient of friction between the block and the surface is 0.30. How far from the bottom of the incline does the block slide before coming to rest? Solve this problem on your own. A 4-kilogram block is connected to a 7-kilogram block by a massless string. The string is passed over a pulley so that both of the blocks are hanging down, as in an Atwood's machine. If the 7-kilogram block is given a downward push so that it is initially moving at 2 meters per second, how fast is each block moving when the 7-kilogram object reaches a point that is 0.85 meters below where it started? Bar charts would be useful, especially since you have to be aware of the kinetic and potential energies of each block in the problem. You have a series of examples similar to this one in your textbook, and you can also look this problem or a similar one up on the internet too. The sum of the energy of position and energy of motion in a system is called the mechanical energy of the system. If all of the forces acting on a system are conservative, the mechanical energy of that system remains constant. In this image, MIT professor Dr. Walter Lewin shows his beliefs in the physics by standing in front of a 5-pound swinging pendulum. This is part of the MIT Open Courseware project, which includes the physics course. Graphically, the work done by a force on an object as the object moves between two locations is the area under the curve between the two positions on a plot of the force versus position for the object. To see this, suppose that a constant force, F sub 0, acts on an object as it moves between x equals x sub 0 and x equals x sub f. If you plot the force acting on the object as a function of position, remember that area below the x-axis is considered as negative area, and area above the x-axis is considered positive area. A 2-kilogram block sets on a horizontal frictionless table. It is acted upon a single force of 3 newtons. If the block moves along the x-axis and has a speed of 7 meters per second at x equals 7 meters, on your own, find the speed of the object at x equals 12 meters. A 5-kilogram object is lifted 3 meters, carried horizontally from left to right at distance of 5 meters, lowered 3 meters, and returned to its original location by moving it 5 meters from right to left. How much work is done by the gravitational force on the object as it is moved through this round-trip path? Remember, you can do work against gravity, and gravity can do work on the object. One is positive and the other is negative work. How much work was done by gravity when you move horizontally perpendicularly to the pull of gravity? The answer is 0. So, make sure you answer the question that was asked. How much work is done by the gravitational force on the object as it is moved through this round-trip path? Mass times gravity times height, approximately 150 joules. The rest of the motion is either not parallel to the direction of the force, or is work done by the lifting and not by gravity. A 5-kilogram object sets on a horizontal table. The coefficient of friction between the object and the table is 0.25. The object is moved from 0 meters, 0 meters to 0 meters, 3 meters to 5 meters, 3 meters to 5 meters, 0 meters, and then returned to 0 meters, 0 meters. The xy plane for this problem lies in the plane of the table. How much work is done by the frictional force on the object as it moves through this round-trip path? there is a path-dependent problem. You will need to know the force and the entire distance traveled, not the displacement and not just the motion down like the previous problem. Do you see the similarities and differences? Friction is a non-conservative force, while gravity was a conservative force. The work done by a force is represented graphically by an area under the force versus position curve. Every force in nature falls into one of two categories, conservative and non-conservative. Conservative forces have potential energy functions associated with them. So now you have gone this far, don't just sit there, use the force and continue on along your journey. A little work can get you far. In this lesson, you cover the following objectives.